let's talk about agenda for today. So today we are going to talk about vectors again. Yesterday I briefly touched upon vectors because I wanted to motivate you with certain examples from machine learning for which you needed to understand what are vectors. Then I'll go on and talk about linear combinations. Then we'll talk about span and then linear dependence and independence. Fine. Cool. So let's talk about the vectors again. So we saw in the last lecture that vectors are quantities with magnitude and direction, and we usually represent them with an arrow. So this is a vector, and we represent them with a small alphabet. So this is one vector. This is some other vector, v, right? And there is some magnitude associated with it, some value, say 2, or some value, say again, -2, the magnitude, right? We also saw that in linear algebra, the vectors are usually rooted at origin. Rooted at origin. And origin is a special point in our vector space. It's a 0, 0 point where all the zeros meet, right? We also saw that we can scale a vector and we can add two vectors. So we saw that suppose I have a vector 1, 2, and I have another vector, say 3, 4. I can add them and I will get a new vector, which is 4, 6, right? We also saw an interpretation of this geometrically in which we saw how geometrically these vectors add up. So this is my vector 1, 2, and this is my vector 3, 4. So what I do is from here, there are two ways to do it. I can just take this vector and put it on top of it, and whatever point I reach is my final vector. Or what I can do is from here, I'll take the steps it's telling me to do. So from here, it's telling me go 3 in the direction of X and go 4 in the direction of Y, right? So somewhere here I'll reach and my new vector will be here. This is what I told you about yesterday. This is linear, this is addition of vectors. Addition or subtraction. If you just do a minus, it will be like you are adding the negative vector of this, right? So we can add or subtract these vectors. Also, we can scale them, right? So we saw that if this is my vector plane and this is my vector A, or say U, and I say 2 of U. So on the same line, I will get double the magnitude, but the direction will remain same, right? So what all we did yesterday was nothing but a linear combination. But before that, when we did scaling, right, we took some values from the space R. Because these values can scale the vectors, these values are called scalars. Okay. So scalars are nothing but values taken from the domain R or the space R. And this will be like -infinity to, -2, -1, and infinity, right? And obviously the real values. There are obviously values in between. So this is the real number line. And all of this real number line is called scalars in linear algebra. Now, when we were adding and scaling these vectors, we were actually taking the linear combination of the vectors. Okay. So let me formally define what is a linear combination of the vectors. So formally, if X is a vector that belongs to Rn, so when I say X belongs to Rn, what I mean is when I'm representing X, I have X coordinate values, right? So I have X1, I have X2, ... I have Xn, right? And when I'm saying y belongs to R. Same thing, y also has some n coordinate values that are used to represent this vector. y1, y2, dot, 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 yn. Fine. And A and B are basically the scalars which belong to the real number line. So when we do AX plus AB, AX plus BY, right? That is called the linear combination of X and Y. So if I just do this, A of X plus BY, which is, let me take another slide, AX plus B. So when I'm doing AX plus BY, it will be equal to X2 Xn plus B of y1, y2, dot yn. Right? This is nothing but, if I take these values inside, will be ax1, ax2, dot, 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 a of xn plus by1, by2, and b of yn. Right? And this is nothing but a of x1 plus b of y1, a of x2 plus b of y2, dot, 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 a of xn plus b of yn. Okay, so this is the linear combination. So when we were adding and subtracting vectors, we are scaling them. If we combine these two operations, we actually get the linear combination of the vectors.
Ma'am, that was A only.
Oh, sorry. Okay. Yeah. Sorry. I made a mistake. Yeah, that's A of xn and B of yn. Right. Fine. So now we have understood what is a linear combination of vector, right? So let's visualize them also. Like what happens when I add two vectors or I take linear combination of these two vectors. Fine. So for this, I'll switch to GeoGebra and the link will be given to you. So this is my GeoGebra platform. So I am first seeing what is the vector 1, 2, 2 looks like on the 2D plane, right? So 1, 2, 2 belongs to R2. So I can visualize this or plot this in R2 easily. Fine. Now I will also plot 2 and 3. So these are two of my vectors which I was talking about. Right. Now let's take linear combination of these vectors. So if you can see, I have taken minus u plus 2v, and this is the vector representing that. Then let me take another combination. So this is minus 2u minus 0.5v. Let me take another combination. Let me and another combination, another combination, and another combination, another combination. Right? So you can see that whenever I take the linear combination, it's going in different directions, right? Fine. So this is clear to everyone, right? When we take linear combination of the vectors, their magnitude and the magnitude and the direction of the resulting vector can be very different from the two of the vectors that we are adding, or three or n number of the vectors that we are adding. This is clear, right? Clear?
Yes, ma'am.
Cool. So we saw that when we take these two vectors, it's going in all the directions. But can I also say something else about this? Or will the combination of these two vectors cover all the vectors that are there in R2?
Yes, ma'am.
Can we say that? We can. So it's is it clear to everyone that we can say that the linear combination of these two vectors will actually cover all the vectors that are there in R2? So yeah. I'm saying when I take linear combination of these two vectors, so these are my two initial vectors, right? When I'm taking linear combination, what I'm doing is I'm scaling and adding them together. I'm getting some resultant vector. For example, when I took minus u plus 2v, I got this vector. So what I'm saying is, what I'm asking is, if I take all the possible linear combinations of these two vectors, will I be able to cover all the vectors that are there in R2?
Yes, ma'am.
Okay, I was not expecting that answer. Okay, why is that? Why do you think that we will be able to cover all the vectors? We'll come to a formal proof of this. But if it's not very evident, let's look at this. Fine. So we saw that somehow when I take the linear combination of these two vectors, my claim is the linear combination should give me all the vectors in R2. This is all linear combinations. Okay. So I'm claiming that if I take the linear combination of these two vectors and I take all possible linear combination of these two vectors, I'll be able to just drop that word. I'll be able to cover all the vectors that are there in R2. Fine. So this is what will I be able to cover all the vectors with these two vectors? Let's see. So before we jump to that particular proof, let's see these two special vectors. Okay, so this is 1, 0 and 0 and 1. So these are very special vectors in linear algebra, and in any space, in any coordinate space, vectors like these are called special vectors. We'll come to that later in future lectures, but let's see how do they look like in the 2D space. Okay, so I'll turn these off. So this is basically the point corresponding to 1, 0, right? And this is the point corresponding to 0, 1. Fine. I can also draw vectors corresponding to that. I can say vector 0, 1. And I can also say vector 1, 1, 0. Fine. So these are the two vectors, right? So let's say I want to get a vector, a very generic vector. I have not specified what is the value of A and B. If I take these two vectors, right, can I obtain A and B, the vector A and AB? So let's call this vector U. Okay. So I'm asking, can I get U from 1, 0 and 0, 1? Can someone tell me? Can I get it? And how do I get it?
Yes, ma'am. By writing the linear combination of A of A vector 1, 0 plus B of 0 vector.
Correct. Right? Fine. So, like Varshita said, everybody clear on this, right? That I can get U vector as A of 1, 0 plus B of 0, 1, right? So this is very generic. I have not specified any vector, right? I have taken a very generic vector. So this means that I will be able to generate any vector in R2 using these two vectors, right? So these are special vectors. And you can just, put the value of first coordinate here, second coordinate here, and you will get the vector that you want to obtain. Fine. But if I have to ask a similar question with this vector, is it that evident? Suppose I want to generate a vector A and B, right? From 1 and 2 and 2 and 3, some linear combination of this. What is this? use x plus y of 2, 3. Right? Let me use this as well. So can you tell me what will be the value of x and y so that I obtain a and b? Is that very clear or is it very evident from these? No, right? Anyone? It's not very evident. It's not very, sorry, Varshita?
If we have values of a and b, then by taking the two equations after solving, if we get the x value and y value to be a real number, then maybe the linear combination may be possible. Not
Cool.
completely, but there
Yeah.
may be a possibility.
Okay, fine. Explanation taken, but there is an easier way to say that also, right? So what if I say that if I can generate 1, 0 and 0, 1 from the linear combination of these two vectors, then for sure I'll be able to generate any vector a and b, ab, right? So what I'm saying is, if because told you and we saw that we can generate any vector ab from the linear combination of these two vectors, right? So if I somehow can generate these two vectors, then my proof is done, right? If I somehow can generate these two vectors from these 1, 2 and 2, 3, then I can generate any vector and it will become very evident, right? So let's do that. So let's do it for 1, 0. So can I generate 1, 0 as a linear combination of 1, 2 and 2, 3? Fine. So this is a very standard way of doing it, which Varshita was also talking about, that we will take the linear combination of this, right? So I will take the linear combination of 1, 2. Let me just slip it in so I can reduce the number of steps. So this is 2a plus 2b plus 3b is equals to 1, 0. Fine. I can also write a plus 2b is equals to, I will take them together, 2a plus 3b is equals to 1, 0, right? And we know this from our 12th class maths that we can write it as, these are basically two equations that we'll solve, right? Is equals to 0. Let me multiply this whole equation with this and do minus here. Then I will get 2a plus 4b is equals to 2 and 2a minus 3b is equals to 0. And there's a minus here. This will cut. B is equals to 2. Fine. And we can do similarly for 0 and 1. So you can do that at your home. And we'll see. Am I getting... Oh, I have not computed the value of A. So B is equals to 2. Let me compute the value of A here. A is equals to minus 2B plus 1. Right? A is equals to minus 2 into 2 plus 1. A is equals to minus 4 plus 1. So this is minus 3. So A is equals to, so I got the values. A is equals to minus 3 and B is equals to 2. Right? I solved from whatever we know in our linear algebra class that this is this value. Fine. So now I can represent. You can do similar thing for 0 and 1 as well. Right? And you will find that these are the values that you'll get. That minus 3 times of 1 and 2 plus 2 times of 2 and 3 is the special vector 1, 0. And 2 times of 1 and 2 minus 1 times of 2 and 3, you will get the special vector 0 and 1, right? So if you don't believe the algebra that we just did, we can visualize this as well. Right? So these are my two vectors. And this is the solution that we have obtained, right? So minus 3 times u is 1, 2, and 2 times v, right? Actually, let me see. Okay. I'm just zooming here. Okay, so can you see? Maybe let me change the color of this so that we'll be able to see this. Okay. So you can see when I took the combination, I got the 0, 1 vector. Then when I took the other combination, I got the, let me change the color of this. I got 1, 0 vector here. And when I took the other combination, I got 0, 1 vector. Right? I will make it more colorful so that you are able to visualize this properly. Right. Fine. So you can see that the linear combinations, certain linear combination of these two vectors is actually getting me these two special vectors. And these two special vectors can indeed generate any vector in the R2 space. Fine. This is clear to everyone. Please unmute and ask if you have any doubts. And if anything is not clear till now. Please unmute yourself and let me know.
Yeah, madam. Yes.
Clear, right? Fine. Okay. Do this as a homework that you actually should obtain A is equals to 2 and B is equals to -1 for generating this. Fine. Fine. So I have proved that indeed all linear combinations of 1 and 2 and 2 and 3 will give me all vectors belonging to R2. Fine. So my claim, whatever I was claiming, I proved that it is correct. Fine. And this is just the summary of this, that since we got 1, 0, 1, 0, 1, and from the linear combination of this, any vector in R2 can be obtained from this, and my claim is correct. And thus, I will get any vector in R2 using the linear combination of these two vectors. Fine. But is it true for any two vectors in R2? Let's take an example, okay? So I am taking these two vectors, 2, 5 and -4 and 10. Let's see what happens. Right? I will also turn off these two vectors. Okay. So this is my vector 2, 5. And this is my vector -4 and 10. Right? So you can visualize, right? So these are two vectors. Can anyone tell me, will I be able to get all the vectors in R2 using the linear combination of these two vectors?
No, madam.
No, right? Why is that?
We follow the same line. So if you take any linear combination, that will also be on the same.
Right, exactly. So if I take any linear combination of these two vectors, it will lie on the same line, right? Let's see that. If I take this is vector INJ, right? Okay. So I'll take 2i plus 3j. right? Or I can do 4i plus 4j. Or I can do a better thing. I'll do some pi plus rj, right? And I will actually switch the values. I will, sorry, p into I. This one, it need to be pi. Minus p into I, right? So this is basically p. This is actually all the linear combinations of these two vectors. Fine. So you can see all of them, like Rohan said, lie on the same line, right? So I will not be able to go out and reach any other vector in R2. Fine. So what is special about these two vectors that I picked here, 2, 5 and minus 4, 10? Okay. So if you observe clearly, you will see that minus 4, 10 is nothing but minus 2 times 2 and 5, right? So it's a scalar, or it's a scaled vector of the first vector that we already have. Fine. So will I be able to obtain 1, 0 and 0, 1 from these two vectors? The answer is no. And you can prove this at home. Just try the same thing that you try to obtain 1, 0 and 0, 1 and see if you can get this. The answer obviously you should get is no, because if you are able to get these two vectors, you should be able to cover all the vectors in R2. Fine. So just do this for homework.